Welcome to our fourth series of our gas laws. Now, in our fourth series, what we're going to go over is the kinetic molecular theory and the ideal gas law. Now, the kinetic molecular theory is what's going to explain why these gas behave in a way that we can extrapolate these gas laws. Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, and Avogadro's law are the five laws that we went over so far. These are basically observations, things that happen in a way that we can notice that always happen the exact same way, but these laws do not explain exactly why they behave in a way they do. And our next, what we're going to go over, the kinetic molecular theory, is the part that's going to explain why these laws behave the way they do, and this will later on be derived into what we call the ideal gas law, which will be our sixth gas law. So, the kinetic molecular theory. Basically, what is kinetic molecular theory? Well, if you were to translate each part of this, kinetic is movement and molecular, dealing with molecules. So this theory is about the movement of molecules. Okay, so specifically, we are dealing with gas molecules, gas particles. So this theory consists of five postulates that are able to explain why the gas particles behave the way they do in such a way that we are able to observe it and come up with our gas laws. So postulate number one, basically, particles of a gas are in constant random motion and collide with both one another and the container. Now, what it's saying is saying that these gas particles are tiny particles. Think of it as, let's say, if we were to magnify it, we're looking at a pool table with pool balls in there, and you were to hit the balls with your white cue ball. What happens is these balls, because it has a cause, they start motion. They all have a direct straight line motion, even though they can be calculated in such a way with the angle, but they will always be moving in a straight line and will not change direction unless there is a cause, such as colliding with other gas particles or the sides of the container or the surface. Okay, and that's our postulate number one in how it explains why gases behave the way they do. Now, our postulate number two is stating that gas is mostly empty space. Well, basically, this comes down to evidence of gas being able to be compressed. Okay, gases they have a massive amount of space between each other, because if you look at the scale, if you look at the atomic scale, the nucleus and the electron itself already has a massive space between them. But if we're talking about gas molecules that are freely moving around at constant random motion, we're talking about the space between these atoms of being a massive distance. And because of that, they are actually considered to have basically zero volume, almost negligible, to the point where they are dimensionless. Until they stack up into a large quantity. This is the opposite of solids, in which they are tightly bound together next to each other so that they are hard to compress. All right, so you can easily notice these examples within a container or a piston that has a sealed end, and you push down on that piston. If it has gas in it, you're able to compress it to a very tight volume. All right, and that is because gas is mostly empty space, and you can narrow down those distance between each gas molecule. All right, and then we come to our third postulate. Our third postulate explains that pressure is exerted when the gas particles hit the sides of the container or the surface. All right, now when gas particles are constantly at random motion, they're always eventually going to hit a surface or the wall of the container that these gases are contained in. And when it does, the force that it exerts, that it creates when it impacts on the surface or the wall of the container, is what we call pressure. The more collisions, the more pressure is exerted upon that surface. All right, this explains how pressure plays into the role of our kinetic molecular theory, which then explains the gas laws. And then we go into our fourth postulate. Our fourth postulate talks about gas particles are assumed not to attract or repel each other. Right? There may be minor London dispersion forces, but overall, these gas particles do not attract or repel each other. If that was the case, then we would be living in a tragic world where the oxygen that we breathe in would be attracting to each other and clumping into giant gas bubbles, which we would have to try and find in order for us to breathe. So luckily that is not the case, and these are always in constant motion, and then those collisions that do occur between gas particles tend to be what we call a total elastic collision, which means as soon as they hit each other, they basically collide and then go the opposite direction with the same exact force that they collided with. All right, that's a complete energy transfer there. Okay, this explains part of how gases behave. And then we go into our fifth postulate, in which the average kinetic energy of the gas particles are directly proportional to that of the temperature of the gas. We're talking about heat, and heat is then transferred and measured as temperature. All right? Now that temperature, when you're heating up these gas molecules absorb that energy and then transfer it into kinetic energy, which is movement. So these particles are moving a lot faster when that is occurring. Hence, the more collisions that's occurring, also the pressure increases as the temperature increases along with the movement of the gas particles. So these are the 5 postulates that are able to explain all these gas laws, and then further on we are able to extrapolate and explain our ideal gas law from this. So what is an ideal gas? Well, basically an ideal gas are gases whose behavior can be predicted by the kinetic molecular theory. Those are what we call ideal, or so-called perfect gases. Right? However, no gases are truly ideal because no gas totally obeys all the gas laws. Because if we think about each of the gas laws we went over, Boyle's law, Charles' law, combined, Gay-Lussac's and Avogadro's law, each of those had a constant variable that was involved, which means if one is constant, then another equation cannot be applied. However, because we're dealing with ideal, we use these laws or these theory postulates so that we can extrapolate to get to such a close value. All right, even though it's not perfect, we can get so close to it, and we can measure the difference between those values and tell how close we are to that of which is perfect. All right, so let's go on to our next one. So when can we get gas to behave the most ideal? Well, since it's not exactly we're not able to create specifically a perfect ideal gas, there are ways in which we can reach optimum and very close to being ideal. And there have been conditions that we found out that would fit this temperature, fit this criteria. And those happen to be when you are at low pressure and high temperature. Here is one of the main reasons why this technically is not viable, because we're talking about low pressure and high temperature. These are opposite values. And according to Gay-Lussac's law, if you have a low pressure, well, technically, if you have lowered the pressure, your temperature will be lowered as well. However, if you want an ideal gas, you would have to lower the pressure and increase that temperature at the same time, which contradicts that Gay-Lussac's law. All right. However, these are the known conditions in which how we can reach that ideal situation. Also, another condition that helps for these gases to behave ideal is that if we're dealing with small particles, atoms that are dealing with smaller masses such as hydrogen or helium, those tend to be the cases in which we can reach an ideal gas. All right. So what does this come down to? Well, this comes down to a conclusion in which we can derive into what we call the ideal gas law. Basically, the ideal gas law combines all of these four variables, pressure, volume, and number of moles, and the temperature, and we use those so that if we have three of those variables, we can find out our fourth variable's value in an ideal condition, so we can get close to it. And that equation we are actually going to learn is PV equals nRT, or sometimes people refer to it as PivNert. We have pressure and volume and number of moles with R and temperature. Now this equation is actually unit specific, which means you must use the exact unit in order for this to work. So the pressure will always be in atmospheres. There are certain equations that you will see that they require you use torr or kilopascals or other values, and in that case our R value actually ends up changing. However, depending on what's given to you, typically ATM is the easiest value that we can come to. V for volume is always going to be in liters. N, number of moles, will always be in moles. If you're given grams, you must convert it into moles by dividing it by its molar mass. And then we have temperature in Kelvin. All right. Now let's look at our value that we do not recognize. Right here we have R. All right. Now in ideal gas law, this is unique because up till now, the 5 gas laws we've learned, none of the constants, the variable constants, have been involved in the equation. Now we are dealing with a case in which that constant is involved in this equation, and that R is recognized as our universal gas constant. Well, what is our universal gas constant? Well, basically, that universal gas constant R has a very specific value. Just like everybody is able to associate the value pi in mathematics as 3.14, if we ever encounter R as universal constant, it has a very specific value that you should always associate it with. And that value for R is going to be 0.0821 atmosphere liter per Kelvin mole. All right? Now this value is always going to be the R's value, and this follows along. Now a common mistake a lot of people tend to make is they think of this part as an equation. However, remember, if it's an equation, they will be written in symbols of P, V, or N, or T, and etc. They are not written as these units, which means this bracket that I'm circling right now, this is strictly a unit. So please please keep in mind not to make the mistake of plugging values into these specific units. This exists here, just like Celsius. If you were to write 10 degrees Celsius, that Celsius is always attached. You don't just plug temperature in there. This is just a unit, and this is what merely that unit is. It just happens to have a lot of units attached to it at the same time. So R is a constant using the P, V, N, and T values. We can actually calculate this using the standard conditions, and that will be for a further another lesson or another example that I'll show you in the future. However, using this, you can apply this to the ideal gas law and calculate it out. All right. So, how can we apply this into a question? Well, let's look at this one right here. How many moles of H2 is in a 3.1 liter sample of H2 measured at 1.24 atmospheres and 293 Kelvin? Well, it's all the same. Identify all the numbers here, and then ask what is the question finding, and then identify each. Liters, atmospheres, Kelvin. You very well know what these units are associated with, and you can then predict this. Considering the fact that this equation or this problem involves 4 variables, there's only one equation that fits that, which is PVN equals nRT. And all we need to do is plug that into this equation right here, and all we need to do is then calculate it out. All right? Remember, notice that R is using that 0.0821 value with the unit along. All right? So this should help you calculate this entire equation. Hope that helped with summarizing all 6 gas laws. Thank you.